much, Manuel. Michael, take it away.
Okay, great. I'm going to move this up a little bit. You guys can hear me, right? I assume? All right. Okay, so I'll get started here. We're running a little behind, I guess. So I'm going to talk about modeling of fluid systems in Dyad. If you don't know what Dyad is, that's not the topic of this talk. But a quick summary is it's essentially it's a modeling platform that we're building out, built on top of Julia. And if you came to our lunch and learn yesterday, you'd have learned all about that, but I'm not going to cover that here. I do want to call out my two co-authors, Venkatesh Prasad, actually Venkatesh Prasad Bhatt, I get that slightly wrong there, and then Avinash Subramanian. I put these superhero figures next to them because they actually, Venkatesh Prasad is responsible mostly for the first half of this presentation, and I would say Avinash is responsible for most of the second half of this presentation, so I'm just here giving it. Anyway, they did a great job, especially in the last couple of days, in trying to pull stuff together for me. So I'll cover some of our goals in putting this together. We wanted to accomplish a couple of things. First, we want to be able to make libraries of reusable component models for fluid systems in Dyad, which is, as I said, our modeling platform, and that would work over a wide range of different media. We don't want to create a component like a valve that's just for air, and then another component that's a valve just for nitrogen, and another one that's just for oil, and so on. That's what we're trying to avoid. And so we can actually map this into two concerns. The first one is creating reusable models of media, and by media I just mean fluids, liquids, gases, things like that. So what I like about our approach is that the media libraries are developed entirely in Julia. That includes the development of them, the testing of them, and the visualization of them. And this allows us to support, the abstractions that we have allow us to support a wide range of different equations of state and different thermodynamic states. So, and I'll show examples of this, so you'll see what I mean. And then we want to be able to support sort of arbitrary collections of properties that we want to evaluate as well. And then on the other side of this, we have reusable components. So there's the model of the media, then there's the actual model of the components. So this is like valves, control volumes, spools, things like that. So there, what we want to do is create generic medium-independent components for, as I said, valves, volumes, pistons, things like that, and avoid re-implementing that same behavior over and over again just for different fluids, because it turns out that this behavior is pretty much independent of the fluid, with the exception of a few points, which is where our abstraction comes in. And we want to be able to adapt to different structural characteristics of the fluid as well. This involves fluids that have speciation, different species in them, or multi-phase fluids. And another thing I will talk about is how we infer what medium to use in a particular component model. And I think we have a nice system for doing that. So let's start with the medium model stuff. So this is a lot of what you're seeing here are things that were developed by Venkatesh Prasad. So we're going to start with a simple example of an ideal gas, and I'm going to just choose diatomic nitrogen because it's the most plentiful thing in this room. So it turns out you could write a very simple Julia function to do this. If you wanted to calculate the density of diatomic nitrogen, it's pretty straightforward. It's just this relationship. And so you might think, well, this is kind of trivial. We'll see where this gets a lot more complicated in a minute. But I want you to all memorize this number because I'm going to show it over and over again. And the fact that it's the same number every time is proof that this system is working. So, if you want to check my work, you just quickly take your memory photograph of that so you can compare it. I just look at it and look for the last 4 digits, 6035. So you could take that shortcut too. There are a couple issues with this function. One is that it's highly specific to diatomic nitrogen. Another thing is that the function signature is kind of ambiguous. I don't know which of these two positional arguments is pressure or temperature unless I'm actually looking at the function signature. So I could reverse them and I get a very different number. You'll note it does not end in 6035. Okay, so let's improve on that. So we can create this abstract type in Julia, abstract medium. And we can say, well, let's just make it so that these density functions take 2 arguments. The first one is an abstract medium and maybe the pressure and the temperature afterward. And that way we can swap in different media for the first part, right? We think that might work. So the problem is these arguments are also still ambiguous. But this isn't going to handle speciation for reasons I'll explain in a minute. And If we then wanted to create a model, a specific implementation of this N2 though, using this sort of an approach, this is one way we could do that. The actual way that we do this involves lots of different attributes of these gases, but I'm trying to keep this simple here. So now, if we do this, we can say, well, for a given ideal gas and a given pressure and a given temperature, we can compute density like this. Okay, so that's a little more generic, doesn't hardwire in the gas constant, for example. And again, remember, the number ends in 6035, so it must be right. But you'll notice that the density function is taking the gas that we're interested in and then these two additional arguments. But we have to get into this topic. In fact, this will be a sort of recurring theme as I go through the media material. Nature's kind of complicated. It's not a linear system, as it turns out, and there's lots of complexities, and this is the first one, which is this notion of thermodynamic state. So it turns out, in the previous functions, we took pressure and temperature as the input arguments. Now, it's probably clear, if you, like, from high school chemistry or something with the ideal gas law, that we're not going to be able to compute the density from just the pressure or just the temperature, right? We need both of them. And you might think, okay, problem solved, pressure, temperature. But no, it's not that simple. It turns out that there are cases where even if you have the pressure and the temperature, that's not sufficient. So the classic example is something like a water-steam mixture. And I'll show a diagram that explains that a little bit more in a minute, but I think we all know that if you're talking about water at 100 degrees C or 0 degrees C, you don't quite know what phase you're dealing with, right? So temperature's not enough. It also, in cases where you have mixtures of ideal gases, for example, the air in this room, we need to know what the ratios of the different gases are in order to compute the properties. So here's a little bit of Julia code to kind of show some of this. The first one is we could define this notion of a thermodynamic state, and we could define one particular thermodynamic state as one that involves pressure and temperature. This works if you don't have any phase changes, so that's the thermodynamic state you'd use in that case. And then this is how we would write it. Now, we've gotten rid of the ambiguity thing now because we're creating this struct, and we can use keyword arguments to construct this, so we can always be sure that we're setting the pressure equal to what we think the pressure is and the temperature equal to what we think the temperature is. So we've addressed some of those problems here. We can calculate the density for a given media and a given thermodynamic state. And so again, the number ends in 6035, so it must be right. With the same approach, we can actually then define mixtures around this abstraction. So we have the next idea here is we can define a new kind of media, which is a mixture that is composed of some set of, some media vector, where each one of these is a medium as well. And you could define air in that way. So air is a mixture of many things, but primarily two things, nitrogen and oxygen. And then you might use a thermodynamic state that looks like this, PT and X. So I need to know not just the pressure and temperature, but I need to know the ratios of those things with respect to each other, which varies based on location, for example, and altitude. So we can then define our density function. It again has essentially the same signature, two arguments, what medium you're interested in and what thermodynamic state you're interested in, but you can see how we can use lots of Julia expression syntax here to essentially compute the density of the mixture in terms of the density of its individual constituents in a nice way. And again, it ends in 6035. So, and in this case, it's because I've chosen an air that's composed entirely of nitrogen here, and that's why it ends in 6035. Of course, if we were to take real air, it would not end in 6035. It's not wrong, it's just, it involves different gases. So, but you can see it's essentially the same sort of syntax for invoking this, what the medium is and what the thermodynamic state is. And this will become important when we get into the component modeling. So a couple things to note. This works for a mixture of any media. That you notice the type here of this vector is abstract medium. So you can pick and choose. And there's a couple caveats. One is that it's only applicable for non-reacting media. So if you were to mix two things together that were then going to explode, this would not apply. Okay, if they're reacting, then they're not independent of each other, and you'd need to do something besides this just simple weighted averaging for mixing. But we are making use of this sort of recursive calling here, where this density then calls another density. And you could even make mixtures of mixtures and so on. Not that you'd really want to, but it's just kind of neat that it would work. And this using broadcasting here is very nice because it just makes it so it's a nice succinct way of calculating the properties of mixtures. Now, I said that nature doesn't really cooperate with this whole modeling endeavor I've been involved with my whole career, and this is a perfect example of what I'm talking about. If the world were simple, diagrams like this wouldn't exist, but sadly, this is actually pretty typical. So this is water, but pretty much everything looks like this. Every sort of liquid-gas combination looks like this. So what this is showing you here is that if you look at these red lines, I think I actually explained this here, let's see. So a thermodynamic state in this particular case is represented not by pressure and temperature, but by pressure and enthalpy. Enthalpy is the true sort of unique identifier of the state of this mixture. So the properties, one of the things I'll point out is there's several properties on here. You can see there's this red line. It sort of comes down here and bends this way, and then it goes across, and then it bends down like that. And these are complex relationships in pressure and enthalpy. No straight lines here for the most part, except right here. And what's going on here is that you're going from liquid on this end to gas on this end. And so it remains at whatever the boiling temperature is for that pressure. And you can see at 1 bar, it's 100 degrees C, which matches, I think, everybody's basic high school chemistry. So this is why temperature isn't sufficient. All of these points here are at a given pressure and a specified temperature of 100 degrees, and yet these are all very different states for this system. And green is the specific volume or the reciprocal of the density, and you can again see it's not a simple relationship as it traverses this diagram. So, and so for two-phase fluids, the bottom line is that you need to use pH for the thermodynamic state and not PT. Oops, and I think I was executing a git command when I was editing my slides. An errant few keystrokes there. So there are a bunch of properties of fluids that we need to concern ourselves with. There are things like specific internal energy, specific enthalpy, the ratio of specific heats, the specific heats at constant volume, constant pressure. That's really the derivative of enthalpy and internal energy with respect to pressure. Yeah, well, anyway, I won't get into that. The ratio of the specific heats. Sometimes you actually, in the case where you have pH as your thermodynamic state, you want to back out temperature, for example. So temperature is something you might want to calculate. And molecular weight is another common thing. So here's a nice little Julia hack that we used in the implementation of this. Cp, which is this specific heat value at constant pressure, is actually the derivative of the enthalpy with respect to temperature. And so while we've implemented the enthalpy function, which is a complex polynomial, when we want to go calculate this specific heat Cp, we can use the forward diff package to actually generate that function because we know it's the derivative of the enthalpy with respect to temperature. So there we go. It'll generate that and presumably generate it efficiently and error-free. So that's kind of a neat feature of Julia. And then we'll calculate the specific heat. It also does not end in whatever I said, 6035, but this is not the density anymore. And that's why. This is the specific heat. So, so there's specific heat. What's cool about doing this stuff in Julia is that we can, it traces through nicely with symbols. So if you use the symbolics package and you call these things, you get the symbols back out, right? So in the case of a mixture, this is this air mixture, and I'm calling this and I'm specifying the pressure and the temperature as symbols, and then the ratios of these two things in the atmosphere as constants, and all that just sort of gets worked out, and I get this relatively simple form for the density, right, in terms of the pressure and temperature for the mixture. And this is important because the next step of this is going to be building component models of these systems, and those component models are built on top of modeling toolkit, which needs these symbolic representations in order to solve the systems of equations. But staying with the Julia side for the moment, there's lots of cool stuff we can do in Julia in developing all this, and one of the things I'm trying to emphasize here is that for all of this stuff, we stay completely within the Julia world. We leverage all the cool capabilities in Julia. So for example, we can create a test suite that tests all of these things, right? And there's our 6035 again. captured in our test suite. But we can go through and create a bunch of essentially reference tests to make sure that all of these sort of known points match for our models, so that we don't have any regressions in the future. So that's using Julia for testing. We can also do all kinds of visualization. This is also quite nice when you're developing these properties, to be able to look at them and to sort of eyeball them and see if they look right. Venkatesh Prasad, who's in the front row here, made me a very nice interactive web application that allowed you to drag the different the thermodynamic state thing around on a slider and update it, and I couldn't quite get it to fit into this presentation. So otherwise I would have a nice interactive demo. So it's a shame that I couldn't figure out a way to get it to work in here. It kept getting the wrong size and occluding parts of the plots, but kudos to Venkatesh Prasad for actually making that work. Okay, so that was the first half of that, which is how do we define these properties in Julia, and what, why is that cool, and why is Julia good for that? The second part is creating these component-oriented models. So what we're aspiring to do here is to build a model like this, right? So some model that involves a bunch of different, like valves, for example, or pipes with heating on them, and here's another valve, and some sort of sources and sinks for the fluid to go through, and so on. And so there's a couple things I want to point out about this. One is that you can sort of intuit as just looking at this diagram, the fact that if there's some kind of fluid in here, then presumably that's what's flowing out here, which is presumably what's flowing in here, which is presumably what's flowing out here. And since these are connected, that's what's flowing in here, and so on, all the way down the line. So we have this intuition when looking at something like this about the fact that these things must be working with the same fluid. Now, the thing is, that intuition and the way we infer this makes sense in the context of like these connections. It seems reasonable to infer that if something's flowing out from here, it's flowing through this as well. It's easy when you have two connectors on a component like this, that presumably whatever's flowing in here is coming out here. But I will point out that there are lots of components that you would have in fluid systems. Heat exchangers are a classic example, where you might actually have two different working fluids involved. And there you can't just rely on automatically inferring that. You have to actually have something that explicitly says, okay, the fluid that's coming in here is flowing out on that side, and there's another distinct fluid coming in from here and flowing out on that side. So you need to have some ability to specify some of these things explicitly. But for the most part, it's possible to sort of infer this information, and that'll come up in a second why we do that. But as I said, some explicit information is required. Now, in Dyad, which is this essentially domain-specific language that we use for describing interactions of physical components, one of the key concepts there is this notion of a connector. So here's the definition of a connector in Dyad. And this will translate down into Julia code, but I'm not going to discuss that process per se. I just want to describe the modeling here. So a couple things to note. There's this external opaque Julia type here, abstract medium. We can just basically say in Dyad, there exists a type in Julia called abstract medium, FYI. We don't know really anything about it. It's just that it exists. And then in connectors, you will typically have potential and flow variables. I'm not going to go into dynamic system modeling, but these are sort of analogous if you're familiar with the terms through and across variables or potential and effort variables. It's the same thing. And these are common across most engineering domains: mechanical systems, electrical systems, fluid systems, thermal systems. But what's interesting about fluid systems in particular is that they have this notion of streams, which are intensive properties of the fluid that's flowing through. So in this case, I'm just showing you enthalpy, which is needed to make an energy balance. And then in Dyad, we have this concept of a path variable. And a path variable is some variable that is essentially shared across some circuit in the system. So whatever kind of system you're talking about, in this case, we're talking about fluid systems, the idea is that if you have continuity through that thing to form a circuit, that every component along there, every connector in that circuit has this same piece of information on it. And in this case, it's the particular fluid model that we're interested in. So Here's an example of a very simple component modeled using Dyad. This is a boundary component where we're going to assume fixed pressure and temperature conditions. So there's some port. These fluid ports are the means by which fluid components exchange information conceptually. So this thing is going to be connected to something through this port, but it's going to enforce the fact that the pressure at that port is fixed according to some parameter, and it's going to compute the enthalpy at that port. So when mass flows out of this component into another component, this is the enthalpy, the specific enthalpy of that fluid, and that is calculated based on this fixed temperature parameter. So essentially it's saying this is an infinite reservoir. Actually, these things are noted over here. This is an infinite reservoir of fluid that is at a certain pressure and temperature, and it's unperturbed by any interactions. No fluid pumped in or pumped out is going to change what the pressure and the temperature are. So it fixes the pressure and temperature, and it only needs to compute one property here, which is just the enthalpy. And the beauty of Dyad, one of the things that if you see any of the material on Dyad, Dyad is for describing the structure of a problem, but it is not. It doesn't have anything in it about describing computations, how actual math is performed. That's all done in Julia. So it outsources all of the heavy lifting for computing or calculation of mathematical relationships to Julia. And so what that means is that you can just basically call Julia functions from within Dyad. And that's what's going on here. We're just calling this enthalpy function that we defined earlier. So here's another component we're going to use in this example, which is a flow component. This sits between two things. So it has two ports, and it's between those two ports that this fluid is going to flow. It has some parameters you can see here. This is overly simplistic. Anybody who's done fluid flow in the audience will probably immediately recognize that this is a very naive model because it assumes fluid flow is linear, which is really never the case. But I just didn't want to get into the complexities of modeling the nonlinear case, so I just made it simple. And this is really describing the mass flow through the linear valve. So what it's saying is that, first of all, there's a statement here, continuity between the two ports. That's just saying that whatever fluid is flowing through A is also flowing through B. The next one is mass conservation. Whatever mass comes in through A is going to leave through B, meaning that there's no actual storage inside this valve. And then you have this constitutive relationship for the flow, which is just a pressure-driven linear flow rate. And then you have the fact that the properties on either side are defined. I'm not going to go into what the in-stream operator is, but just we need to define properties for different flow directions, let's just say, and how those properties are propagated. And then the thing is, the enthalpy is flowing essentially through this system. It comes along for the ride, but you notice we don't actually compute any fluid properties in here. We're just getting them from one side and passing them along to the other side. Is effectively what those last two equations say. And now finally, this is the last component that I'm going to show you, the sort of fundamental component, which is a simple control volume. Again, it interacts with the fluid parts of the system through this fluid port. It has a bunch of characteristics. It has a volume. It has an initial pressure. It has an initial temperature. It has a time-varying mass, time-varying total energy, and a time-varying temperature inside of it. This is where the dynamics in my system are going to come from. We have some initial equations here. We have the calculation of the mass, the internal energy, and this enthalpy, all using different functions in Julia, right? So these are all based on the medium and the thermodynamic state. And I probably say some of this over here. Yes, we use three properties. We conserve mass and energy. We specify initial conditions, and it's a fixed volume, so there's no work term. But we could easily add one. Okay, here's our complete system. It's a boundary, a linear valve, and a closed volume. And at the highest level, we need to specify what fluid property we're actually dealing with. So we got three components. We choose which particular medium we want to be in this system at this level. We use this continuity statement to essentially inject that into our circuit, and then from there we can infer this across the entire system. So we only have to specify this in one place, which makes it nice and easy for the modeler. And we can infer it everywhere else. And this actually includes a regression test, which I used extensively in the development of this to make sure I wasn't screwing something up. And it includes an analysis that's going to perform a transient analysis of this model for 10 seconds and test the filling of this control volume. So what's happening is we're starting off in this system with a sort of 10 bar pressure in this boundary, and no, actually, yeah, and then, I don't know, I think I maybe missed a digit here somewhere when I did this, but I think this is actually supposed to be 100K. I think I messed it up when I copied it to the slide. But anyway, high pressure in the bound, on the boundary, low pressure, relatively low pressure, atmospheric pressure in the control volume, and then the valve allows the control volume to fill, is what this is. And you can see what's going on there, and you can see I was right. It starts from atmospheric pressure. This is in pascals, and it goes to 10 atmospheres up here. And you sort of see that's the filling of it over time. Those are the results. So, so to recap, so as I said, there's sort of two dimensions to this work. One is, I have to say, a lot of the stuff that we're doing in terms of the modeling of the fluid in Julia is inspired by the way it was done in Modia, which is another Julia package, which has a sort of common ancestry with some of this work. And these fluid properties are developed completely in Julia. It's very nice. It gives you, you have all the nice Julia tooling and libraries to do that. We can use things like automatic differentiation. We can leverage multiple dispatch so that we have a single function in enthalpy, densities, internal energy across all the different media that we use and across all the different thermodynamic states that we use. We do testing and visualization in Julia. So that's all fun and great for the medium side. On the component side, what I want people to appreciate is the fact that the medium itself is a sort of model in and of itself, right? And it's actually, it spans this system. So it's kind of snaking its way through all of these circuits, but we want to have the ability to build a system of physical components and then still have the ability to decide to use different media inside of there. So, so that's, we're essentially swapping different models of the media out. We're leveraging connectivity to intuitively propagate information about what medium is actually present in all of these places. And when you can author components, as a result, you can author components in such a way that those components will work sort of independent of what the particular choice of medium is. And I didn't show any examples of speciation or multi-phase stuff, but that'll be sort of, will further that work. But I just didn't, it was already quite a bit of material to cover. Anyway, so the point is that our goal here is to really develop a library of fluid components that can be used across a wide range of media. And the other thing is that ultimately, in this case, you just develop you can develop these property functions as you need them for particular components. You see that some components required 0 properties, some required 1, some required 3. So what you need to develop is really just the union of what all your individual components require. And yeah, only need to support thermodynamic states, you'll need the same thing. And the property evaluations are just invocations of ordinary Julia functions in the end. Oops, and that's not the slide I wanted to show. But anyway, there's a slide that says thanks, and I don't know why it showed that other slide, but I made a mistake.
Thank you so much, Michael. That was quite a half an hour. Yeah.
Yeah, I think yeah, I didn't go over either.
No, you did great. You did great. Like we lost a little time because of some technical difficulties earlier. So, but you helped us more or less make it up. So, thanks. Okay. Yeah, let's thank the speaker and.